Okay, welcome to section 4.4. We're going to talk about periodic functions, stretching, and translating graphs. And this is critical material. It really leads to the stuff we're going to be doing in trigonometry. So this is big. Objective. We're going to determine the periodicity and amplitude from graphs, to stretch and shrink graphs both vertically and horizontally, and to translate graphs. You want to be an expert at those things after today. So, why do we have periodic functions? It is because the world is full of periodic phenomena. All right? My family, this many years ago, we're at the beach. And at the beach, when you go to the beach, what do you see? The tide coming in or going out. That's because tides are periodic. The tides come in and go out again and again, each cycle or period lasting about 12.5 hours. Also, another beach picture, by the way, all right? And that, I believe, is my daughter with my Labradoodle Roxy and my Havanese Bella. We spend a lot of time at the beach, as you can see. Anyway, the amount of daylight. You know, we're getting into the dead of winter right now. The days are getting shorter. And then as we go on towards the spring, the days will continually get longer and longer and longer. That's because the amount of daylight on any given day, the function that would represent that is periodic. The amount of daylight increases and decreases with a period of 1 year. The functions that describe periodic behavior are called periodic functions. So, a function f is periodic if there is a positive number p called a period of f such that f of x plus that fundamental period p equals f of x. And you guys know if you add p to your x value in a function, all that is a horizontal translation, either right or left, depending on the sign of p. Like if p is a positive number, this plus p would translate the function f of x p units to the left. And because this function is periodic and the fundamental period is p, that would slide the function right on top of itself, so you would be looking at exactly the same graph. So for all x in the domain of f, the smallest period of a periodic function is called the fundamental period of a function. So f is a periodic function with period p implies f of x will always equal f of x plus any multiple of that fundamental period, x plus np, for all x and any integer n. So we can go either direction. N could be a positive integer or a negative integer. All right, so find the fundamental period of f and then find f of 99. Okay, well, let's first talk about the fundamental period. This is a piecewise linear function right here. All right, and when I am asked to find the fundamental period of a function, I start at the y-axis, and then I'm going to follow the curve until I see that the pattern is repeating itself. And it looks like this distance right to there, okay, that pattern is being repeated over and over again in both directions. So that tells me that this function has a fundamental period of 1, 2, 3, 4 units. The graph takes 4 units to complete one period. Now, I cannot see what f of 99 is on this graph, but I do know that it is periodic and its fundamental period is 4. So there's an easy way for me then to find f of 99, and I simply will do this. Well, because f of x equals f of x plus any multiple of p, well, if I take this 99 and I divide it by the fundamental period of 4, And that's because, okay, if this pattern just keeps repeating, all right, then I do this division and I find the remainder. So how many times does 4 go into 99? Well, 4 times, what would that be? 24, that would be 96. So 99 divided by 4 would be 24 with a remainder, okay? And again, 4 times 24 would be 80, 96. There would be a remainder of 3 right there. That tells me that f of 99 is going to have the same output as f of this 3. So f of 99 equals f of 3. And now I can just look at this graph, and f of 3 is 1, 2, 3. That point right there, which has a y coordinate of -2. f of 3 equals -2. Now, you're going to have problems that take you the other direction too. That's okay. Same thing. Now we're looking for f of -99. So I'm going to take my -99 and divide it by the fundamental period of this function, which is 4. And that's going to give me a -24. And what's my remainder this time? It's going to be a negative number. Now 4 times -24 would be -96. And I need -3 more to get to -99. So my remainder is -3. So that implies f of -99 equals f of -3. Now I can look at the graph. -1, -2, -3. What is this output right there? +2. So f of -99 equals f of -3, which equals 2. Okay, find the amplitude of the function. Now amplitude, you're going to get really good at this. And amplitude is nothing more than half of the range of the function. So I see it already because the min of this function is -2, the max is 2, so this range would be 4 units, and 1/2 of 4 is 2. But there's a simple formula for amplitude as well. Amplitude will always be A equals the max, which we use a capital M for, minus the min, which we use a lowercase m for, divided by 2. Because the max minus the min gives me the range of my function. And if I divide by 2, I get half of that. So let's do the arithmetic. What's the max of this function? 2. Minus, what's the min of this function? Well, what's that y value right there? -2. 2 minus -2 is 4, and then I divide that by 2, and 4 divided by 2 equals 2. So that piecewise linear function has an amplitude of 2. Stretching and shrinking graphs. If you go into a house of mirrors at a circus or carnival, you may see your reflection distorted by some of the mirrors. For example, one mirror might make you look tall and thin, while another might make you look short and broad. Just as mirrors can stretch or shrink your reflection both vertically and horizontally, it is possible to stretch or shrink the graph of an equation, both vertically and horizontally. And we need to become experts at that. So, the graph of y equals c times f of x, where c is positive and does not equal 1, because if I multiply anything by 1, I'm not changing it, is obtained by vertically stretching or shrinking the graph of y equals f of x. So if I take my function and I multiply it by any number c that does not equal 1, I'm either going to stretch the function vertically or shrink it vertically. So, let's play. I want you to conjecture. This piecewise linear function in red is y equals f of x. So what do you think y equals 2 times f of x would look like? All that is going to do is take every output in f of x and multiply it by 2. So it's easiest to see if you look at the extrema. See that 2 right there? Well, if I multiply that by that scalar factor of 2, it's going to jump to 4. And do you see this -2? That now multiplied by 2 would jump down to -4. And every other point on that graph is going to do the same thing. We are multiplying this entire function by 2. So you'll notice that the x-intercepts won't change, but every other y value on that piecewise linear function is being multiplied by 2. So that's going to stretch it vertically, just like that. And now that note that we just verbalized, notice that the points on the x-axis remain fixed. They did not move. While all other points move away from the x-axis for c greater than 1. And that's a vertical stretch. Now on the next diagram, I'm going to show you what happens when c is in the open interval between 0 and 1. And here we go. So now, here's our original piecewise linear function with an amplitude of 2. But now we're going to vertically shrink it. So how about if we go, instead of y equals f of x, let's go y equals 1/2 of f of x. So that's going to take the extrema, which was 2, half of 2 would be a 1, and half of -2 would be a -1, and that's how I'm going to vertically shrink this function right here. The intercepts on the x-axis will stay the same, but every other point is being multiplied by 1/2, and so we get that diagram right there. And notice here, okay, the points on the x-axis have remained fixed again. They did not move at all, and that's because 0 times 1/2 is still 0. But every other y value of every point on that graph has been multiplied by 1/2. So we did a shrinking towards the x-axis because c was in the open interval between 0 and 1. c in this case is 1/2. All right, now the graph of y equals f of c times x, where c is positive and not equal to 1, because again, if I multiply my x-coordinate by 1, I am not changing anything, is obtained by horizontally stretching or shrinking the graph of y equals f of x. So, if we multiply the entire function by a number other than 1, we change the amplitude. We do a vertical stretch or shrink. If we multiply our independent variable x by a number not equal to 1, we're going to change the graph horizontally. We're going to either horizontally stretch it or shrink it. So, one more time, this is our same red piecewise linear function with a period of 4. And now we've taken that function and it looks like we have horizontally compressed it. So the period of this function would be, well, let's follow the curve. It only takes 2 units now for the pattern to repeat. So this function has a period of 2. Now, very simple. Okay, what is my c to make that happen? And again, all you need to know is this number c right there will always divide the period of my original function f of x. So that number divides the period. So if the period was 4 and the period now is 2, it looks like my c would be 2, because 4 divided by 2 would give me that 2 right there. All right, now let's see. Notice that the points on the y-axis remain fixed. So my y-intercepts did not move. Those are the only points on the y-axis. But every other point on this graph was compressed towards the y-axis. That's a horizontal shrink. While all other points move toward the y-axis for c greater than 1. And in this problem, my c is a 2. So that caused a horizontal shrink. And we'll talk about the rest of this on the next example. Okay, now look at this. We still have our same piecewise linear graph with a period of 4. And now what have we done? We have horizontally, stretched the graph. So what's the period of this one? Now, if I follow it, it looks like I have to go all the way to the end. So how far is that horizontally? 1, 2, 3, 4, 5, 6, 7, and 8. So the period is now 8. All right. So what C is going to make that happen? Now remember, this number C is going to divide the period. So what number would I divide 4 by to get 8? And wouldn't that be 4 divided by 1/2 would give me 8, because 1/2 goes into 4 8 times. So that's a 1/2 right there. And that's all there is to that. Okay, now notice that the points on the y-axis still remain fixed, both of those points at the origin, while all other points moved away from the y-axis because our C was in the open interval between 0 and 1. It was 1/2. And that's going to cause the horizontal stretch. Wow, this is good stuff. So, let's see. The red graph is a periodic function of f with a fundamental period of, and this is our same piecewise linear function, and that period hasn't changed. It is still 4 units for that pattern to repeat. And the amplitude, well, is half of the range, and the range of this goes from -2 to 2. That's 4 units. Half of that would be 2 units. And we have a formula for that amplitude. Amplitude is always max minus min divided by 2. Or in this case, 2 minus -2 is 4 divided by 2, 2. Okay, now, what do we have here? We have a vertical stretch of that graph. So express the black graph in terms of f. Well, all you have to do is focus on, like, your max was 2, now it's a 4. Your min was -2, now, or it's a -4. So it looks to me like we took every point in the function f of x and we multiplied it by 2. There you go. So simple as that. Notice that a vertical stretching or shrinking of the graph affects the amplitude but not the period. The period of this black graph right here is still 4 units. All right. Now let's do something else. Okay, let's do a horizontal shrinkage of the graph. Now, that's hard to see right now, so picture our original piecewise linear function that had a period of 4, and now we want to compress this graph horizontally. So now look at this piecewise linear function in black, and what's this period? It looks to me like it only takes 2 units now for the period to complete itself. Right there, 2 units. So now I'm going to have to take my x and multiply it by a number c. So the period of that black piecewise linear function is 2. All right, and the period of our red piecewise linear function was 4. Remember now, this number c divides the period of my original function. So let me see. Well, the period is now, was 4, but it's now 2. So that's going to make this c a 2. And there you go. Notice that a horizontal stretching or shrinking of the graph affects the period, okay, but not the amplitude. The amplitude of this piecewise linear function in black is still 2 units. All right, so changing of the period and amplitude of a periodic function. Highlight this and understand it. This pays off big when we get into trigonometry. If a periodic function has a period of p and an amplitude of a, then y equals c times f of x has a period of, well, this c that I'm multiplying the whole function by is not going to affect the period. So if the period was p, it's still p. And the amplitude, well, it was a, but we multiplied the function by c, so now the amplitude would be c times a. And y equals f of cx. Well, this c, we're multiplying the independent variable x by. All right? So that is going to not affect the amplitude, but it will affect the period. The c divides the period, so if the period was p, the period is now p over c. And the amplitude stays the same. The amplitude will still be the a right there. Oh, that's so big. Okay, now let's get to translating graphs. Okay, this looks like your typical cubic right here. Y equals f of x. And it looks to me like this is y equals f of x, but we have slid it both horizontally and vertically a little bit. So how do we deal with translating graphs in the plane? All right, it's very simple. Let's pick a point that we can clearly see on the original function. We'll call that xy. All right. Now, what's the corresponding function on our corresponding point on our red graph? It would be right there. All right. Now, what happened? Well, we took our original graph in black and we translated it h units to the right. Okay, so guess what? This is x translated h units to the right. So this is x plus h, all right? And then we took it and we translated upwards k units. So we're going to go y plus k. So that would be the coordinates of this point. But now, how do we deal with translations in the plane? Now remember, if I translated k units up, then my y here, I'm going to have to go minus k. And think about that. If you added k to both sides, you'd have a plus k over here, which would translate the graph k units up. Now the same thing occurs with my horizontal translation. If I translated h units to the right, then I'm going to have to go f of x minus that h. All right, there it is. So if this function in black is y equals f of x, then the function in red would be y minus k equals f of x minus h. Now, our parent function, the parabola, y equals x squared. Let's translate. All right, now look at what we did, and I see scale on this one, so we can do the perfect equation for this red parabola right here. Okay, what are the coordinates of this point? Well, the x-coordinate is 2, and the y-coordinate is 1. All right, so it looks like I translated 2 units to the right and 1 unit up. So my translation, my vertical translation of 1 unit means this is going to be y minus that 1. And then my horizontal translation of 2 units to the right would be x minus 2. Remember now, in this notation, like the minus means I translated horizontally to the right. How far? 2 units. The minus means I translated vertically up. How far? 1 unit. All right, so we're almost there, you guys. Let's sketch the graphs of the following equations and let's put them on the same coordinate plane. So we're going to start with the parent function of all absolute value functions, y equals the absolute value of x. Now remember, that is the v function. Y equals the absolute value of x. There it is right there. Pretty good graph. Done by hand on PowerPoint, by the way. Now, if I take y equals the absolute value of x and I rewrite it as y minus 2 equals the absolute value of x minus 3, that means I'm going to take this graph and I'm going to translate it to the right 3 units and then up 2 units. So see this vertex? Let's just go 1, 2, 3, and then go up 1, 2, and put a point for that vertex right there. Now let's go ahead and draw our absolute v with the vertex at 3, 2. And there it is. Now, On the next one, we have no vertical translation because I just have y right there, but my horizontal translation plus 5. That means I need to take this absolute value function, and if I go y equals the absolute value of x, that's now y equals the absolute value of x plus 5. That means I'm just going to take this vertex and translate 1, 2, 3, 4, 5 units to the left. I hope I counted those right. Yes, I did. And that is, x is now from 0 to -5, and my y is 0. And let's put our v function with that vertex right there. Beautiful. Okay, now this slide right here gives you everything we have talked about in this lesson on one side. If the equation y equals f of x is changed to y equals the opposite of f of x, well, that's a reflection in the x-axis. How about y equals the absolute value of f of x? Well, that absolute value, the function f will be unchanged when f of x is greater than or equal to 0, and reflected in the x-axis when f of x is less than 0. How about y equals f of negative x? Well, that's going to be a reflection in the y-axis, reflected in the y-axis. How about x equals f of y? All we did there was interchange the variables. So that's a reflection in the line y equals x. Look over here, reflected in the line y equals x. And then the stuff we started working on today, y equals c times f of x, where c is greater than 1. That's going to be a vertical stretch. Y equals c times f of x, where c is in the open interval between 0 and 1. That's going to be vertically shrunk. And then here, y equals f of c times x. Notice I'm multiplying the x by the c. And if that c is greater than 1, what does that do? That divides the period. So that's going to be a horizontal shrinkage of that graph. And if my c is in the open interval between 0 and 1, that's going to stretch my graph horizontally. And then finally, what we finish with are translations. Y minus k equals f of x minus h. Well, that minus h means I'm going to take the graph and translate it h units to the right, and then minus k units up. So translated h units horizontally and k units vertically. And I'm going to assume the h and k are positive, so that minus tells me I'm translating to the right. This minus tells me I'm translating up. All right, so you guys are going to do 4.4, 1 through 5, 7, 9, 10, and 19. I will post even answers in our Google Classroom, and you do these problems carefully. You've been introduced to this stuff before, but now you have to be held accountable for it, because this leads to trigonometry, which is right around the corner, and this is very big. Become an expert at the stuff you saw today in 4.4, periodic functions, stretching, and translating graphs. Thank you.